So for the Tech Talk today, we are going to have Professor Patrick van der Smagt, and he's a founder of the Machine Learning Research Lab of Volkswagen Group in Munich, also an ELLIS Fellow. And in this Tech Talk, Patrick is going to talk about robotic control using generative machine learning. I hand it over to you, Patrick.
Thank you very much. And if possible, I would really like if a few people keep on the cameras, because it's like been doing these talks since COVID, and I always fall asleep of my own voice when I don't see anybody reacting. So that would be great if a few people would do that, and I don't feel so alone. So thank you.
I keep camera.
I'm going to do show some technical stuff, and my story maybe starts with this video which was made in 2011, and what you see here is Kathy Hutchinson on the right, and Kathy has had a brainstem stroke 4 or 5 years prior to these experiments. No, more like 10 years prior to these experiments, and has a brain implant in her, what we call the motor cortex. And what this thing does, it relates the spiking frequency of the neurons in the motor cortex to the movement of the robot in a training phase. And after that training phase, and it takes about, I don't know, 10, 20 minutes or so, then we use the opposite. So we use the spiking frequency of specific neurons to relate that to the movement of the robot, and that allows her to control the robot to do this simple but for her very relevant task. But this is completely controlled by her brain implant. Now, as impressive as it looks, it's also crappy in a way, right? It's not good enough, it's not fast enough, it's difficult, and this kind of human-robot interaction has always been an issue. Why is the gap between machines and biology so big from a performance point of view? And I'll give you a few insights on that. So, difference in performance, right? Where does this difference in performance come from? Looks impressive, but it's completely model-based. Both of these are completely model-based, but the one on the left learns a model, and the one on the right uses a predefined model.
Let's turn it on, and when we turn it on, it'll take just an instant to stabilize. And fortunately, we have the constant set right, and there we have now the stabilization of an unstable system.
So both parameter-based systems, but the one on the right is completely engineered, and the one on the left is actually older than the one on the right. So that could be done by those systems before the technical systems could do that. So if you look at that, you can sort of summarize that technical systems, and that's not true for all technical systems, but most technical systems are controlled by very simple PD controllers or PID controllers, where your control signal is based on an error in your planned trajectory, between the planned trajectory and the actual trajectory performed by the system, and the difference in those two reference signals that error is multiplied by some constant and used as a control system. It's a very stable system. The nice thing of it is that it is it can be guaranteed to be optimal and stable in certain cases, but certainly stable in certain cases. And the optimal is not so true. For that, you've got model predictive control, and that's the systems what the systems on the left use is where you have an internal forward model of what your controlled, your body is going to do, or your body with the environment is going to do. And it uses an internal optimizer with that forward model, so simulation of the system and the environment. Once that prediction of what would be happening in the future is good enough, then a control signal goes out and creates a new state that's then going back. So you've got two feedback loops here, the one simulated, which happens in the brain, and the rest involves the rest of the body. So the one on the left is predictive, and stability can be guaranteed, but that's really a question, and you need a model. And the one on the right is reactive, and stability is guaranteed under certain circumstances, but it can only react by very, very fast feedback loop. And now, in cases like this, it's really quite impossible to write down a model and a set of equations that allow you to perform like any of the cortical animals are able to do, right? Maybe they cows, but if you can have this predictive model, but you need to do that. So, the one on the right, we call it a machine learning discriminative models, where I have specific examples of whatever system I am going to predict and I'm going to model. And typically that's done through engineering, but you can also do it by supervised learning. And that's a very old thing, right? You predict P of Y given X. So the prediction of the output given the input. And that's something that has been solved in the years 2006 to 2013 approximately. These things have been solved and are very stable. The one on the left, for that, you don't have this trainer, you don't have that desired output, you don't know which control command you need to perform, and for that we use what we call generative models. I know that many people with generative models have this kind of different connotation nowadays, and it's still generative models, but the term is much wider in the. So let's look at this wonderful example. Second University of Vienna in, I think, 2011 approximately. Wonderful stabilization of a system with one actuator, but with those three poles. And how is it done? Well, in the old-fashioned way that you saw on the right, or the engineering way, I should say, that you saw on the right, having the equation of this dynamical system, solving those, and from that compute the optimal control. Are you raising your hand to ask a question, or is that no? Okay, good. Feel free to do so, of course. I'm describing that now in terms of a few boxes that I'm going to use throughout this whole talk. We call them Z, and Z is the state of the dynamical system. And that is, for instance, those three joint angles, but for this system, it's also the joint angle velocity. So it would be, for this case, a six-dimensional vector that describes the state of that system, and that allows you to control that once you know those equations and can solve that through inverting those equations. It's a relatively straightforward, not simple, but a relatively straightforward thing to do in engineering. So in my notation, I say, well, I know that my state at time t+1, my system state at time t+1 depends on my system state at times t. So that's the arrow you see, this arrow, plus a control command, u, right? So zt+1 equals a combination of zt and a u t. And so what we did in the lab, thought, well, okay, let's do that. And ta-da, this is like 11 years after the other thing that you saw before. We can do this as well, right? Highly impressive with 1 degree of freedom. And I understand if you say, well, what the hell? I've just seen that in a much more complex thing. But the difference is that in this case, we don't actually use the measured joint angle. So we don't have that ZT that you saw in the previous equation or not equation, but graph. Is that, so we don't have that. Instead, we use images of the pole. So the only input to the system is the image of the pole. And what we want to attain is a certain image, future image in my pole position. And we have, of course, the commands that we put in the motor, but we don't have the actual joint angle. Now, how does that work? It's very straightforward. It's still the same thing. So I've got that ZT is to ZT plus 1 with my UT, but I furthermore have an X. And my X is not the joint angle, but it is an observation, in this case of the pendulum, and in this case it's the image of the pendulum while it is moving around. So it's a sequence of videos that goes from X0 to X whatever 100 or whatever. And I know that my initial picture of the pendulum needs to go towards a future picture of the pendulum through those transitions from ZT to ZT plus 1. So I know that a certain sequence of joint angles will bring my pendulum to the down position to the upright position. How do I do that? Right, and this allows me to predict the future because I can compute actually the ZT plus how many, whatever, to that X. And the funny thing is that all of these arrows that you see in here are in fact neural networks. Now, what this thing does, it trains the change of pictures in time through the structure, through the sequence of neural networks. And when I say from ZT to ZT plus 1, that's just a recurrent connection. So each of those at one time step is the same neural network that is then feeding into itself again. And if I train this in this way, and I give you details in the next slide how that's going to be, actually my system is going to discover the dynamics of this pendulum by just looking at a sequence of pictures of that pendulum, how it's moving from ZT to ZT plus 1. And the dynamics are actually, there's a graph, two graphs on the bottom. The left graph is colored by the joint angle of the pendulum, and the right graph is colored by the joint angle velocity of the pendulum. So you see it separates joint angle by joint angle velocity by itself by just, again, only looking at the sequence of images that it sees when the pendulum is moving. And I can use that to predict what the pendulum would look like if I'm moving on this landscape. And this is half how this works, and I'm not going to go through the equations here. I think the major takeaway message is that it is an autoencoder, and an autoencoder means that I input here at the bottom, I input my image, I output my same image, and in the center I say, here you have to please make the most compact representation that you can think of. How do you know it's most compact? Well, that's the equations on the right, and I'm happy to explain those. It's a known system from published like 10 years ago, it does that. An example of how that works at autoencoder, what we did here is we used a number of tactile sensors. You can see those fingers here. Those tactile sensors give these kind of signal. It's a 14-dimensional signal that comes out of them, so 14 measurements, giving some kind of information on how these fingers are touching that cup. If I put in just these data into that autoencoder, what it creates is single neurons in that middle layer that represent perpendicular values, but independent values of my data. One is the pitch of the finger, so the pitch is like, I think this movement, I always forget which one it is, and the other is the roll, I mean that movement or whatever, I always forget pitch and rolls. And a third one represents the grip force. It never knew about that, but it distills those, what we know as physical quantities, because it creates the most compact representation in single neurons of that neural network. So you can then use that, and we say, well, okay, so you have this autoencoder, And we know that my system state xt is supposed to correspond to some dynamic representation of my system I call zt, right? The image has to represent or correspond to a certain joint angle velocity. And I roll that thing out in time, and I say, okay, I know that some filter, some transition brings my system from zt to zt plus 1, and so forth, right? And that goes on many, many steps. And now what I can do is very straightforward. I can put in my images at time t and t plus 1 and t plus 2 and so on. And I can just do a simple, straightforward backpropagation through all of these things. And that filter can be a neural network. It can also be some differential equation or something else, some system equation if I want. I just backprop through this whole structure, and backpropping through that whole structure gives you then that barrel's representation of the joint angle, of the dynamics of your system as you've seen before. So it's very, very straightforward. Once you've set up those equations, right, and done that backprop, and have a modest data set, and you can train that thing. So in the example you saw before, we actually didn't use a neural network here in this transition, but we used a Kalman filter. The reason of using a Kalman filter is that you make sure that this transition in your middle layer, and I call that the latent space, my Z space, the latent space, are actually linear. Why do I want those to be linear? Well, that makes my control equations much easier and allows me to apply a much broader range of control algorithms. Quan, you see, I lied to you, I'm not only using videos, so all good. So I have that system, and let's talk about 3 research questions. First of all, how do you train these systems, and how do you extend these systems, and where are the problems? The second, how can I use these in a control setting? And the third thing I want to shortly talk about is how can we actually use that in spatial reasoning? First, and this is highly technical. I'm just highlighting some of the things that you are encountering when you do that kind of stuff. So I mentioned about this dimensional reduction. How do I map a very high dimensional vector x, right, which is for instance an image, but it can also be audio or something else. How do I map that to a very low dimensional 2, 3, 5, 10 dimensional space? And if you do that, then you run into things like you see here is that paths that you define in your space are actually going to cross. Now, crossing paths doesn't matter in the representation, but it matters once you do sampling in here. So suppose I'm here at this cross point. What's my next best point in the dynamics of my system? Is it going up, or is it going to the left? That's a problem. You don't know that unless you have a good trail of states. But if you don't have that, then that's hybrid problematic. So we defined a way of actually separating that by improving on the sharpness of the representations that you can get there. Technical thing. And you see then that this is for a human movement thing, that you get nicely separated path in your latent space. That was for the static case. We can also do that for the dynamic case, where you have sequences of data, as in the second thing I showed, and in each of those, and this is for different kind of model, the extended Kalman VAA, the deep Kalman smoother, and our own deep variational Bayes smoother or filter. And you see that on that data of the pendulum that I showed, that it nicely separates the entangled spaces into nicely disentangled spaces, and you can do control much more stably. Another problem. If I put those data into a low dimensional space, neighboring relationships are not being kept. And that means that points that look very similar in my observation space, so like images that are very, very similar in just a small space, can actually get moved around in this folding of my towel in a low dimensional space. And to show how what happens there, This is a very simple representation in such an autoencoder of actually the 10 digits 0 to 9 in handwritten digits. And if you just train that in that thing, they get nicely separated, right? This is the 1 or something like that. Here's the 0, and the ones which are similar are close to each other, right? For instance, the 8 is close to the 3, the 8 and the 3, because they look visually similar. But then if I say, okay, I want to go from this point, from this 1 to that point, to the 3, how do I do that? And to show you what happens here, if I go take the straight path, the yellow path, and you can see what happens to the digits. It goes from 1 to 8 to 1 to 8 to 5 to 3. Right? It's not the path you want. So it's very difficult if you want to use it in a control system. You have the system, your robot, for instance, will make really weird jumps if you do that. So instead, take the same path again, but do the shortest in terms of the Mahalanobis distance, and you get a straight one in this space. Not in this space, but you get a straight one in your observed space. The trick is you don't only look at the distance in this space, but you also look at the derivative of your internal space, of your latent space with respect to your observation. Here's the math. I'm not going to focus on that, but people who know this kind of differential math and who know about Jacobians recognize easily that it's just a very simple Jacobian squared that is in there, and the Jacobian represents the curvature of the internal representation versus the observed data. And you minimize that and the problem is solved. You can combine those two, and what you get there is by combining that prior that I showed in the beginning, and the latent space smoothness, and the latent space smoothness is now input by putting a penalty on the magnification factor that we showed in the previous equation, and you train that whole thing, and you get nicely smooth spaces. Now, an example of where I can use that is this one. It's a bit of a silly example, but it's tracking objects, and in tracking of objects, you have, of course, the problem of occlusion. Objects disappear, but with this, you can predict where they should be going, and then you can even pick them up, even if they are out of sight for a while. Now, sounds like a silly application, but then we thought, well, you can actually use that to do prediction of human movement. And in this case, what we did, and that's I think in 2020 exactly, that's what it says there. So 4 years ago already, what we did is we took this system and we used that to predict the sound that a drummer makes. And we had a concert in Munich with that. It was in the middle of COVID, so it was an online concert. But the advantage being that now we have this. I can show you this. And what you see here, bottom left is a human drummer. And what he does is he plays his drum. The system, it's a MIDI drum, so the system gets input from his drum set, uses that to find a point in latent space, right, in the same autoencoder approach that I showed before. That point in latent space is then used with this trick you saw in the previous slides to predict the next most likely one, the nearest one in the observation space. It plays it back to the drummer, so the drummer hears what the latent variable model is playing back, and so together they make a jam session. And it sounds like this.
the right, you have the trajectory of the latent space, right?
On the right, you see the trajectory in the latent space. That's correct, yes, in a 3D. Yeah, so the one at the drum and the other is the latent variable model prediction. That should be the next thing. Okay, so we've got that whole setup in place. Beyond making music, what else can you use it for? And so what we did here is we thought, well, let's take exactly the system, and this is really exactly the same implementation, but we used it to control a drone. What you see here is first part where the onboard PD controller of the drone is letting it fly about in this box, and it will hit the walls once in a while. That's why we had to build our own drone, because drones typically don't like that. It also has 24 LiDAR sensors, 8 at the bottom, 8 at the top, and 8 at the side. And we learned the dynamics from this. Now, once we've learned the dynamics, what we can do is use exactly this latent space, put a control on there, using a, actually, I think that's the second part, yes. Actor critic, where we use the onboard sensors to let it move to a certain point in sensor space. So it has to move to a certain point where the sensors tell them it's so many meters away from the wall and the floor and the ceiling. And it can do that after just 30 minutes of gathering information on the dynamics of the drone. So that is rather stable and allows you to learn that dynamics straightforwardly. Same algorithm, different robots. This is exactly doing the same thing, but in a seven-dimensional space, excuse me, where the robot is moving from point A to B in its joint configuration space. It doesn't look very interesting at all, but it's just showing that, yes, this algorithm scales to more complex dynamical systems. And also, if you can do that, then you can do the following as well, because you say, well, okay, I've learned the dynamic of that thing, and on the left, you see just the standard robot control for this, where the robot moves a straight path from point A to B. And the second one, we've learned that dynamics, but also learned the energy cost by just putting a multimeter on the power consumption, and learn then the most energy efficient point in A to B to get the energy about in moving this robot. Don't see much, but that's how it works. And so what we use this for instance, in Volkswagen, is to learn the energy consumption in air pressure controllers in one of the largest plants of the world. Maybe it is the largest, I don't know exactly. And in that, air pressure control is used to control the tools of the workers. And we are able to save in the order of 10% energy in the control of those compressors. And we're talking about 8 compressors, each of those in the size of a small house. And save 10% of the energy consumption of those things with a total cost in energy reduction of about $1 million per year for just one plant. The same algorithm scales to different use cases in toy environments, but also in real environments. The next problem, is getting, again, slightly technical here. The problem is, okay, once I have the control of such a system working on an object, I have the problem, how do I do multi-agent control, right? I've got multiple agents working on the same object. And the trick is to use, again, the same approach where I have this encoder, this autoencoder system, which has an encoder, creates the latent space. In this case, we call it VC, and it goes to the decoder again. But each of the agents has a different action space that is related to them. And we can, first of all, do the learning thing where each agent have their own observations, but a shared set of latent actions, which leads to an own set of actions for each agent. And then we can use that to do the control. Again, the policy is shared by each of those and then used. And this is what allows you to do that. And in this case, we define the policy not with respect to the robot arms, but we define it with respect to the object. So we define how the object has to move from one point to the other. And if you use 2 or 3 or 4 agents, it doesn't make any difference. They will learn that relationship between the object movement and what they have to do to collaborate here. So there is no coordinated action for each of the robots. Each of them is controlled independently of the other, but together they work together to move that box. And of course, it was also done with real hardware, and it works just as well. Okay, still a relatively simple dynamical system. So we thought, okay, well, the next problem we need to do is to jumpstart that on more complex dynamical systems. And in those cases, you need sometimes to start your control system with a initial good guess of what your controller looks like. And the way to do that is typically through imitation learning. So you imitate human or other expert workers to give you the information there. The problem is it doesn't scale, right? It's very costly and so on and so forth. So we thought, well, let's do that from videos. And what the system does, it uses videos of actions to learn this kind of movement. And this case, this is for walking. And you see, well, just look at the video here or at the results down there if you want. The one in the middle is our thing that's pre-learns from videos from other walkers and then learns a policy directly on top of that, and it's much faster in learning the optimal policy or the best policy. Optimal is a hard word, but the best policy to control those walkers. It's work in progress, but it works for these relatively small systems already. Let's skip this. But not this one, because the previous thing you saw on transferring policies from simulations to real systems actually something that is not very well understood. And what we found is that the choice of action space, so how do I control my system? Do I put in joint torques? Do I put in forces? Do I put in velocities? Do I put in positions? Is actually a very important decision that you have. And fast forward to the results here. What we did is two tests. One is I want to go to a certain point in my space, and the other is I want to push my object to a certain position on the table. And what you see here is that in simulation it learns very well, but once you then take the simulated results where you train on, then put it on the real hardware, it's actually a big difference what kind of control space you see. And the one in fat and in bold are the best results. And you see that in many cases, velocity-based control is very stable, works very well. But for instance, a joint velocity Cartesian position only works in one of the situations. So you have to be very, very careful on that. And that allows you to improve on the results of your simulation to real results. Summary and graphs, I'm going to skip that. Planned work is to look into generalist agents. So how do you make generalist agents in the same way of thinking as you have in large language models, right? In large language models, you train by predicting your text based on your context. In generalist agents, you train by predicting your model output based on your sensory input. And the idea is to have kind of training systems where you collect large portions of robot data and use that to create generalist control agents that allow you to kickstart your traditional controllers. Work in progress. Third topic and the last topic, I've got like 5 minutes left approximately, and I think I will make that. How do we use these systems, these latent variable models that I've been preaching the last 40 minutes or so, to allow an autonomous agent to act optimally in an unknown physical world? Now, and what we did is we took, again, exactly the same system, and you see only the output part. You see your sequence of Zs, your sequence of internal beliefs of what where your system is, and you see your observations, your X's, and you see your U's, your actions. But what we added here is a set of M's, and M is a map. And the map is actually a physical map. Like a physical map, it represents the physical 3D space around you. And this extension, adding a map, allows you to do the following, to do state estimation, so to know where you am, to know what your ZT position is and how that corresponds to a point on the map. To do exploration, where should I go to get maximum knowledge of my environment. To do mapping, to know where the other objects or maybe even other agents are. To do prediction, to know what's going to happen if I put in a sequence of actions, and to do planning. Now, very shortly, the stuff, why we put all of that into one thing. First is the state estimation, and by using this probabilistic Bayesian approach, neural network-based Bayesian approach, allows you to get a state estimation by computing your transition factor t from your one observation to your next observation, and that's just a stochastic gradient descent to do that. So that's straightforward in this neural network systems. Exploration, again, very straightforward in this probabilistic system, because you can do that by computing the mutual information between two states through the map. And the exploration then allows you to go to that place where your mutual information gain is going to be maximum. The mapping is very straightforward, again, a neural network implementation, which makes it very fast to get your camera view and your occupancy and color information on your system. Your prediction is very easy, because you can walk through your Z space by a sequence of actions U. So you can put in your planned actions, see how your system is going to react to that, what it predicts that the next place is going to be in your Z space, and therefore also on your map and what you're going to see there. So that's very straightforward in this thing. And finally, you can use that to do planning in that map, for instance, with the A-star search. So compared to traditional SLAM algorithms, which do basically state estimation, this integrated approach that we use allows you to do all of those things into a probabilistic world, and you solve the whole SLAM and the problems around that in one go, basically. We have the tendency to implement everything on hardware as well, which we try on software. So we got a Quasar car a few years ago, and this is all work from the last years. Got a Quasar car a few years ago, allowed it to drive around there, and this is what happens. So the learning is actually in real time at 4 Hertz. It creates a map in real time while it is driving around. And let me skip to the next one. And then that allows it to actually drive around in that maze. And what you see here is actually not the recording of the of such a driving around sequence, but this is actually what it thinks it would see if it would be driving around there. So this is all artificially generated data of that Quasar car based on the previous learned movements. So it's not a recall, but it's a neural network-based representation of its beliefs. And then, of course, you can use that to have it drive to a predefined point that is putting it down. This is the planning algorithm that in the A-star formation to the center of the space. And that's my last technical slide.
So have you finished your presentation? So,
I have finished my presentation because the rest is going about different topics.
okay, yeah. Okay, thanks a lot, Patrick, for very interesting technical and very entertaining talk.